Hello, this is E637. I'm Charles Bouman, and we're here on Monday, so we've caught up on our lectures, I believe. And last lecture I left off with aliasing and sampling, so we're going to take it from there. Are there any questions? Any concerns about the labs? There was one very minor correction that I posted that Jordan asked me to post that just said that you don't have to use XV for the segmentation lab output. Excuse me? Oh, there was one minor correction to the lab for the segmentation that at the very, very end that Jordan had me post. It's actually an adjustment based upon the fact that we're not using XV, that software package that we used to have more easily available. Okay, so is everybody okay with the labs? Are they keeping up? And okay, so let's get off this sampling. I'm going to use a computer today because I brought the wrong notebook, so I have to. So I'll use those notes from the screen. So as I went over this last time, but let me just sort of do a quick review. So basically, in a sampling system, you have a continuous time input, you sample it with a period t, and that produces a discrete time output. And sampling systems are sort of a canonical way of converting continuous time information to discrete time information. And so they're linear systems because if you scale the input, the output scales equivalently, but they're not time invariant. They're time varying linear systems because of the sampling periods are distinct in time. So, in the time domain, the relationship between the signal and its sampled version is quite straightforward. So you'd say, well, why not just leave it there? But this doesn't give you a lot of insight into the question of how do I, from the samples S of n, construct G of t. So in other words, it's easy to represent the forward model here, which is that the output is just the sampled version of the input. But it's not so easy to represent the inverse. How do I take Sn and generate Gt from it? And that's going to be reconstruction. So to get a lot more insight into that question, we can take it into the frequency domain. So this is continuous time. So the Fourier transform in that domain is the continuous time Fourier transform. And this is discrete time, so the Fourier transform here is the discrete time Fourier transform. You can't take the continuous time transform of a discrete signal. Now you can, so the question is then how do you relate the continuous time transform of the input signal and the discrete time Fourier transform of the output signal? And the formula that relates them is this right here. I mean, we can derive it. The derivation isn't too difficult. But I guess just staring at it, it looks like kind of a bit of a complicated formula. So the question of what it really means is a little unclear. But it turns out that it has a very simple interpretation, really. Well, first of all, the sum from minus infinity to infinity of k here is put in there to ensure that the discrete time signal's Fourier transform is periodic with period 2 pi. Because the discrete time Fourier transform of any signal has to be periodic with period 2 pi. So it wouldn't be possible to say that the discrete time Fourier transform was just equal to the continuous time Fourier transform, because the continuous time transform is not periodic, generally speaking. So some conversion has to go on to take the non-periodic signal and make it periodic. And that's what this sum is. Because each term of the sum is shifted by 2 pi k. So this is just like the rep function that we covered before. So by replicating it with period 2 pi, you get a periodic function. Okay. Now, assuming that the signal's sufficiently band limited, there won't be any overlap between those replicated functions. So you can just look at the case for k equals 0. You can look at the case for k equals 0. I was just going to say, it's too bad I can't write on here because I guess it doesn't have an edit feature. The professional version has an edit feature, but this doesn't. Okay. So I can just consider the case where this term here is 0. the 2 pi k is 0. So just consider the k equals 0 term in the sum and ignore the others. And in the case without aliasing, that will be representative. Okay. So in that case, there's only two things that's happening. There's a scaling of the omega axis, and there's a scaling of the signal afterwards. Okay. So this is just an amplitude factor of 1 over t. As the samples get closer together in time, the amplitude of the signal at DC increases. That makes sense because if you take more samples, the total sum of the samples increases by the factor t. Okay. So by the factor 1 over t, right? So here, let me just flip back to the intuition behind. So you have here that s of e to the j omega is equal to 1 over t times g of omega over 2 pi t, right? And this is valid for omega less than pi if no aliasing. So if there's no aliasing, that's a valid relationship, but only for omega less than pi. So here you have pi minus, this is minus pi, and this is pi, and this is 0, okay? Now, if you had a signal, this is in frequency. If you have a signal in time, so this is t, right? And say the signal looked like this. Oh, I don't know. What should I make the signal? I'll just make it like a rect function, okay? Okay, so maybe it goes from minus 1/2 to 1/2, and it's of amplitude 1. So if I sample at period, if I sample at period t, right, then the number of samples will be, the number of samples I'll get here the signal is of length 1, approximately, right? So the approximately, so S of n here, right, is equal to g of nt, right? And the sum over n of S of n is going to approximately equal to 1 over t, right? So in the frequency domain, this is f, and this is omega. So this would be g of f, and this is g of, and this is s of e to the j omega, right? So if the amplitude here is, say, I don't know, is 1, right, at DC, then the DC represents the integral of the signal, so, okay? So it was 1 because the area under this pulse was 1. But when I sample it at period t, the sum is going to be proportional to 1 over t, so that so you're going to get some kind of thing like this, and the amplitude here is 1 over t. So that's what the 1 over t factor is. That's that factor, okay? It just accounts for the gain, the shift, or the gain in the DC term, based upon that if you take more closer samples together, you get more of them, okay? Now, the other thing that happens is that you have this sampling frequency. So the sampling frequency here, that arrow isn't pointed to quite the right place, is f of s over 2, and then here this would be f of s. Okay, so this is going to be f of s over 2, and this is f of s, okay? Well, when you divide by 2 pi t, then what will happen is, so let's say you're at the frequency f of s over 2, so f of s is equal to 1 over t. So if you're at the frequency, let's say you're at the frequency pi, okay? So if I plug pi in here, I get pi over 2 pi t, okay? So the pi's cancel out, and I get 1 over 2t. Let me just do that calculation. I'll do it on a separate piece of paper so I don't mess this up. So if I get omega over 2 pi t, evaluated at omega equals pi, all right? That's equal to pi over 2 pi t. So that's equal to 1 over 2t. That's equal to fs over 2. Because 1 over t, fs is equal to 1 over t, right? So half the sampling frequency corresponds to omega equals pi. So when I look at this frequency, this is omega equals pi, right? That frequency, omega equals pi, corresponds to fs over 2. That's there. All right. So basically, all this formula. So there's three things happening in this formula. One is that you have the sum over k. If there's no aliasing, you don't have to worry about that as long as you're only looking between minus pi and pi. There's the gain factor. The gain factor accounts for the fact that as you take more samples, the ZC gain is greater. So that's just a constant gain. That's not too. Oh yeah, it's very important because it completely changes your result. It's like the interplanetary probe that crashed into Mars because they forgot to convert meters into feet or feet into meters. Okay, so in that case, it's a very important conversion. You know, you may have spent the last 50 years developing new quantum theories of reality so that you could get the probe there, but if you converted meters to feet incorrectly, it still crashes onto the planet. Okay, so everything's important. but like this is pretty straightforward. Okay. But then the other thing that happens is you scale omega, okay? And the scaling omega also depends upon the sampling rate, right? If you sample at a higher frequency, then higher frequencies map to pi. Pi is always half the sampling frequency, so pi goes to half the sampling frequency, okay? So when all said and done, the key relationship is that. That, you know, here you have omega, and here you have f. Okay, so when the digital frequency is 0, the analog frequency should be 0. This is under no aliasing conditions. Okay, if the digital frequency is pi, the analog frequency is fs over 2. Pi corresponds to half the sampling frequency. If the frequency is 2 pi, then this is fs. Okay. Now, if you're anywhere in between, you're just at some value omega. Okay. Well, then here it's going to be omega over 2 pi t, which is actually equal to omega over 2 pi times fs. Right. So this is the scaling relationship. And now, so everybody's clear on that? So going back to the computer, here, let's see. Oh, it's interesting. It'll get stretched out on the screen, doesn't it? Huh. I wonder if I could do the opposite kind of stretching here to compensate it. But anyway, okay, so this just says the same thing. Okay, so this is visually what happens. This is here. The axis here is in units. This is f. This is what I could call continuous time frequency in units of hertz, cycles per second. Once you've sampled something, it no longer has units of cycles per second because there are only samples. It's kind of unitless. So there's cycles per sample then. You could have cycles per sample, which would be unitless, or you can have radians per sample, or yeah, I guess radians per sample or something like that. Anyway, so this is omega. It's unitless axis in units of radians. And this is in units of hertz. Okay? And the conversion between them, because the units have to work out, is in terms of the sampling frequency, fs. So that's the thing that converts. So half the sampling frequency here goes to pi, and 1 goes to 1 over 2. All right. So now you can generalize that to 2D, and now there's sampling periods in both the x and the y dimension, assuming you use a rectangular sampling grid. So it's pretty much the same thing, and this is what the picture looks like. So let's say that you have a square here, and this is half your sampling frequency in the horizontal direction, and this is half your sampling frequency in the vertical direction. So you replicate these with the appropriate distance, okay? And now, half the sampling frequency always goes to pi. So it could be, for instance, you sampled along the y-axis at a much higher rate than you did along the x-axis. Okay, so if you did that, it would look like this. You can switch to my paper here. If you did that, it would look like this. There would be, let's see, oops. So let's say you had a situation like this. This is half the sampling frequency. You've sampled at a much higher rate. So if you sample at if your period's smaller in time or in space, then the frequency is larger, right? So if you use a very small sampling period or a very high sampling rate, okay, then this becomes, oh, let me draw it up here. This becomes one half, I'll call that F sub V for vertical, okay? And I guess, and then maybe this is like this. This is 1/2 F sub U for horizontal, because we use U for the horizontal variable. So then what will happen is that basically you can represent all the frequencies. Oops, I messed that up. You can represent all the frequencies in that rectangle. But when after you sample, then you go to pi. Yeah, I guess that's pi. This is minus pi. This is pi. This is minus pi. Like that, okay? So this rectangle maps to that square because pi is pi. Pi represents half the sampling frequency, whatever that is. So coming back to the computer again, you get this kind of replication, and as long as there's no overlap, then this function equals exactly that function. So all the information in the frequency, I mean, if you have this function, you can certainly calculate that function, right? So this function contains all the same information as that function. Now, that wouldn't be true if there's overlap. Because there's no overlap, they contain the same information. So if the frequency transforms contained exactly the same information, then the signals in the time domain or space domain must also, because there's a one-to-one relationship with them, because it's an invertible transform. So basically, if you don't have aliasing, you can get perfect reconstruction. The way you would get it is take this thing here, calculate that, and then take its inverse Fourier transform. But that's kind of messy. So we'll talk about how to do it more simply. You know, it's a lot like the tomographic reconstruction problem, where we first talked about the Fourier slice theorem, and we had a theory for how you could reconstruct the signal or how the signal contained the information. But it wasn't a very practical method for inversion. And then we came up with a more practical method for inversion. Well, we're going to do the same thing here. And then we're going to talk about reconstruction and how it can be done more practically. Now, if there's aliasing, the reconstruction is a problem. And if the signals extend beyond these cutoff frequencies, half the sampling frequencies, then there's going to be overlap. And the overlap will cause distortion that can't be removed. Now, one of the things that's kind of interesting is that it turns out that a signal doesn't have to be band limited. Okay, so well, maybe I didn't lie, but I certainly misled you, okay? I don't know, maybe I did lie. The signal doesn't have to be band limited to half the sampling frequency in order to reconstruct it. After I said this so many times, to say this now, it seems like, oh gosh. You know, it's like I've lost all trust in anything you have to say. Okay, but see, I never quite said that, really. Or maybe I did. You probably can get the evidence now to show that I did. But what I basically said is if it's band limited, you can reconstruct it, okay? But it's not necessarily the case that it has to be band limited to reconstruct. In fact, even in the 1D case, here, switch to my pad and I'll draw this. Okay, you could have the following, and this happens. So let's say you have a signal. Okay, so this is 1/2 Fs, and this is 1/2 Fs, right? And then you have Fs, and you have 3/2 Fs, right? And let's see. I'm going to get this all messed up probably. So let me see. So if I have a signal, I better be careful here. I have a signal, and I have the signals has frequencies like this. So this is G of t. Now, if you have signals that look like this, so this is minus Fs, this is minus 3/2 Fs. So if that's what your signal looks like, tell me something about this signal. Excuse me?
It's almost as if you've taken a Hilbert transform of this.
So what do you know about the continuous? So this is actually this is not G of t. This is actually G of e to the j omega. Okay. E to the G of f. I'm sorry. That's G of f. Okay. So this is f here, right? So if G of f looks like this, what do you know about G of t?
It's complex.
It's got to be complex, right? Because if it was real valued, what do you know about the Fourier transform? It's got to be conjugate symmetric, right? What do you know about the DC value of this signal, or the integral? What if I compute, this is G of t dt. What's that equal to?
0.
That's equal to 0. Why?
It's all 0.
Because G of 0 is 0, right? Okay. So this is a complex signal, but the theory still works. I could sample it, everything kind of goes through. But can I reconstruct this signal when I sample it at sampling frequency Fs? Because this is not band limited to 1/2 Fs, right? After I sample it, what do you think it's going to look like? So this will be pi, 2 pi, 3 pi. This would make it a great exam problem. 5 pi. And actually, this is practical too. This is important. In fact, this was a huge problem back in like the early 80s. This is 2 pi, minus 3 pi, minus 4 pi. So what's the signal going to look like after it's sampled? So this would be, this will be omega, right? And this will be G of e to the j omega. Oh, no, S. I'm sorry, S of e to the j omega. So that's the sampled signal, right? Well, you know that 1/2 Fs has to go to pi. But I actually kind of lied to you. Well, the k equals 0 term, this thing would be way out here. Okay, so let's see. So it's going to be, Fs is here. So that would be here, right? And then it gets replicated with shifts of 2 pi, right? So this point here goes to where? So I take this, shift it by 2 pi and add it. Shift it by 2 pi and add it. Cha-ching, 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 cha-ching. It's like some kind of like assembly line stamp press thing, as the thing's going through. Have you ever seen the Lucille Ball episode where she's like working an assembly line making the candies? Okay, this is real. Okay, we got a few aficionados in here because somebody's seen that. Okay. For all the you that have not seen that, you have to go see that episode. But anyway, okay, so you have to shift by 2 pi and add. Shift by 2 pi and add, okay? Right? So where will happen when you shift by 2 pi and add? What's this function going to look like? Which way should we shift, left or right? Does it matter?
Both.
Both. Okay. So I'll go left first. okay, because that one's more interesting. So if I shift this by 2 pi, that goes here, right? And then it's going to look like this. Okay, and then I'll do it again, 2 pi, okay. Oops, I'm not drawing it so well. 4 pi, okay. Now I can shift this way, Now what do you know about this function, S of n? This is the frequency function, but its inverse transform, the S of n is in time. What do you know about it? If it has a transform that looks like this, what do you know about that signal in time? It's going to be complex. Right? And, okay, so I can actually, maintained all this information, right, in this discrete time signal. Now what I could do is we're going to learn about Reconstruction Theory, okay? So we could basically use impulses to produce the signal back again. We haven't gotten there yet, but believe me, it's going to happen in just a few minutes. And most of you probably already know about this already. So this will be, again, 1/2 Fs, 3/2 Fs, 2 Fs, 5/2 Fs, right? Same thing here. So what will happen is that we'll be able to produce this again. Is that a perfect reconstruction of this signal? Well, no, because this looks clearly different than that, right? But then what you're going to do is you could put a filter in, and you can pick off that one, and you can get rid of these. So I'll cross them out. And voila, you've reconstructed that signal, and I violated the Nyquist criteria because it was not band limited to half the sampling frequency. But somehow the spirit of the Nyquist criteria has been maintained, right? Because its total bandwidth. The total bandwidth was less than half the sampling frequency. In fact, in this case, the condition is that the total bandwidth has to be less than the sampling frequency. Okay, so sure, we could do that. Yeah.
So, a little confused for the last one, because the second one is replication, so probably last one should be comb version of that.
Should be excuse me?
Comb.
Oh, comb. Oh, comb. In the time domain, that's true. So before I filtered this thing out, when you go to do the reconstruction, what you do is you take the discrete time signal. We're going to talk about this in just a minute. And you use the discrete time signal to modulate a train of impulses. So it looks like a comb. That's exactly what it looks like. But when you filter that signal to remove just this one thing, after that, then it doesn't look like a comb anymore. It looks like basically the signal that the comb envelope traced out. So it puts you back here again. So this is actually very important because you can actually demodulate a signal. Because this could be a modulated signal. You can demodulate a signal with sampling. But to do that, you have to have a very fast sampler because it has to be able to have an aperture that can sample at the carrier frequency. So usually what you do is you demodulate first because that's could be more cheaply done with, stably. And then this may bring it down to the IF frequency, they call it the intermediate frequency, and then sample that. And it gives you more accurate separations of what they call I and Q channels.
Professor?
Yeah.
How do you know you should filter that part of because the aliasing happens maybe. So if you use the filter, how do you know you should filter exactly that part of the...
there's a few answers to that question. One of them is, well, obviously it kind of looks like the same piece, okay? So that's the intuitive answer, okay?
Yeah.
Okay. The other way is you could write all these terms down mathematically, and you'd see that this one corresponds exactly to that. Okay, I'll let you do that as an exercise. But yeah, it's...
What if you do not know the signal frequency?
Then you got a problem.
Yeah, that's what I mean.
Yeah, so the real key issue in sampling is that you have a constraint on the signal that you know it only exists in some, it has some limited bandwidth, and you know where that is. Or, it may not even, the classical formulation of Nyquist sampling is that it's band limited and you know what the range of non-zero frequencies is. There could be an extended version of that where you have to estimate the range of non-zero frequencies. But yeah, it's a good question. Yeah.
Professor, how do we apply this filter, which has frequency response beyond FS? How practically do we do that?
Well, this is a high frequency. This is an analog filter, right? So one answer is you design an analog filter with a high frequency, a high center frequency. Okay. That could be tricky because it requires that you have a lot of very precise capacitors and inductors and so forth. The other possibility is this: you could pick off this frequency here, and then modulate it up with a mixer. You'll get the same result. That's probably how people would more likely do it. But when you do that, then the carriers have to be coherent and precise, or you'll get phase errors, which may or may not be important. If it's a communication system and you have like phase, you've encoded information in the phase, then that would be important. So this could be like a what do you call it? A relay, not a relay, a repeater in a communication system, where this was a modulated signal and it took it, sort of demodulated, amplified it, and retransmitted it. Yeah. It's kind of interesting. It does come up. Okay, let's come back to the slides on the computer. So the Nyquist sampling condition is stronger than really is necessary. You can have more complex sampling. You can violate the Nyquist criteria and still be able to reconstruct the signal, as long as you know what it is that the bandwidth of the original signal was. And this comes up in imaging applications because the bandwidth of the image may not fit into like a square or a rectangle, particularly if one of these axes is time. So what happens in time? Let me just come back to I'm going to just go through this really quickly. And there's at least. Oh, by the way, just to remind you, in preparation for the test, which I think is at the end of next week, I have basically homework assignments on the web page. Okay, so they're all exam problems, and you should do them. And there's some exam problems which are based on exactly this stuff. Okay, so but in images, what happens is there's a thing called interlace and progressive scan, which you guys probably know about because when you buy your TV sets, they actually talk about it now. Okay, so I don't know if you've heard of 1080p, and there is like 1080i. You don't see 1080i very often because actually, I'm pretty sure, at least this was the marketing information, that HD. Now, what was the competing technology to Blu-ray? It was HD CDs. DVD. DVDs were 1080i, and Blu-ray was 1080p, and that was one of the reasons that I think these things often have a lot more to do with the commercial negotiations that occur behind the scenes. But from a technological point of view, the Blu-ray had some advantage because it stored a little more data. I mean, really, any format it's just a data storage format, really. Although there's some subtleties probably. But for the most part, it's a data storage format, so you can store anything you want, but the data capacity was a little higher in the Blu-ray, so they could put 1080p. Okay? In progressive scan, you get basically, so this is X. So let's say this is X, and this is T. Okay? So in progressive, you get, you take samples. I'll put little X's here. Okay, it's not going to be the greatest drawing ever. Okay, so you get, and the samples are in the same place. Let me make this Y because it's a little more intuitive, because it's actually along the vertical axis that this occurs. But you, in progressive scan, you sample all the lines of the image simultaneously at every time, and usually the sampling time, if it's standard, say, is usually 1/60th of a second. So you get 60 frames per second. Each frame has full resolution, right? But so this is progressive. Okay, then there's interlaced, which is what NTSC video is, the older analog standard that nobody's using anymore now, I guess. So here what happens is that what you did is you said, okay, well, every other time I'll take the alternate lines. So the first frame you get, say, the even lines, and the second one you get the odd lines, and you get even, odd, okay? So let's say that if there's 1080i, what it would really mean in each of these frames you get, what's half 1080? 540. You get 540 lines, okay, which is basically what NTSC used to be. You get 540 lines, but every other time you shift them up a half a sample or down a half a sample. So you get, so if you take two, so each of these is called a field. And you put two fields together and you get a frame. So two fields equal a frame. So people would argue, they'd say, well, is NTSC video 30 frames per second or 60 frames a second? Well, it's both, okay? Or no, actually it's 30. Or they'd say, well, is it 60 or 30 images per second? And the answer, well, it's sort of both, okay? Because it's 30 frames per second, but it's 60 fields per second. So in the frequency domain, so in this case, the 1080p is better than the 1080i because you have more data. I mean, if all you care about is fidelity of the representation and all other things are equal, then the 1080p is better than the 1080i because you're getting more data. You know, whether that data improves the image or not, well, it's a separate matter, but it's certainly not worse. Okay. But the disadvantage is that the progressive scan is less efficient because what happens is that you have basically a diamond pattern here. So in the progressive scan, in the frequency domain, the frequency ranges you get are like this. Okay, so this is what you might call, this is horizontal frequency, which I guess is new, right? And this is temporal frequency, which I guess we'll call F. Okay, so whereas in the interlaced, you get something like this. That's the frequencies that you can represent. So you get like a diamond pattern. So what this says is that if you have a stationary scene, then you get the full resolution here of the 1080 lines. In other words, if you have a fixed thing that's not varying, then you get the higher spatial resolution. But if you have something varying rapidly that's got low spatial frequencies in it, then you get the higher spatial frequency. So this is for half the number of samples. For half the number of samples, you get almost the same coverage, because the theory is supposed to be that this stuff out here doesn't happen that often. Things that move fast and change rapidly and have high spatial frequencies in them, that you're visually not sensitive to that, so you don't care so much. So you could have made this like number bigger and used Interlace and had a lower, at the same data rate, produced maybe a higher quality image, because this could be a more efficient format. But the other problem with Interlace format is it's just sort of complicated to deal with. For instance, if you have computer vision applications, people don't like Interlace, because you don't have, if you want to do differential subtractions of frames, it gets complicated because you have to do interpolation. So people like progressive for that. It's simple. It's kind of simple. So, okay, so that's the difference between Interlace and progressive. And it's very much related to this whole sampling theory. Okay, now, let's see. Okay, now, focal plane arrays. So could we switch to the computer? Over the years, the focal plane array technologies have changed a lot. When I first started in this business, people were still using Vidicon tubes, which are like well, I don't know if you remember what a CRT is, okay? It's a TV, okay? It's like one of those things where, it's made out of glass and it weighs a ton, okay? So those kind of gone by the wayside now, and flat panel displays have really pretty much taken over. But they used to have TV picture tubes that they basically kind of ran backwards, and they're called Vidicon tubes. So where they use the photons of the light to discharge electrons that they would then measure, okay? Those things tend to be kind of nasty. They were heavy and they saturated pretty easily. They had a lot of various kinds of problems. I mean, it turns out tube technology is still preferable in some applications where you want to count photons at very low light levels. But Vidicon tubes have pretty much gone to the wayside, and they were replaced by CCDs, which are called charge-coupled devices. Now, CCDs are still analog devices, but they're analog devices on silicon. And, each CCD cell counts photons, and then what happens is that they have what they call a bucket brigade sort of a technology, where they have switch capacitors, and the switch capacitors basically can shift charge around through various tricky maneuvers, okay? You know what a bucket brigade is, right? Bucket brigades, what they did, I think it was invented by Benjamin Franklin in Philadelphia. Maybe it wasn't, but we take credit for it, you know what I mean? I'm from Philadelphia, so it probably was invented somewhere else, but we'll pretend it was invented there, okay? So, and what happened is that, Philadelphia, the old original Philadelphia city, it was near the Delaware River. And what would happen, of course, somebody's house would catch on fire, often during the winter, right, because of the sparks from the fireplace or something like that. So they formed a consortium where if you paid a certain amount of money into the system, you'd have a little plaque on your house, and it meant you belonged to the club that tried to put the fire out, okay? So then everybody, if you had that plaque on, everybody would come over and they'd all get in a line, and they'd try to carry the water from the Delaware River by handing it across from one person to the next, rather than having to get one bucket of water and run all the way up. That was very inefficient, because you're transporting not just the weight of the water, but also the weight of your body, okay? So it's a bucket brigade here, that each cell transfers the charge from one cell to the next charge, and it's like a shift register, and it shifts it to the right, and then what it will typically do is shift it over one row, and then shift it, and the last row is designed to shift it down. And then there's an analog amplifier at the end so it basically generates a raster scan analog signal. Now you can pass it into an A to D converter, and you digitize it and store it in a computer, and then it's digital. But it's intrinsically an analog signal. It's very high dynamic range, and it's there was something else. There's problems. There's some limitations in terms of dark currents and things like that. Yeah, it's kind of been the mainstay for high-quality imaging. But it doesn't allow to have random access. More modern technology that's really, I think, replacing CCDs slowly, although in scientific applications, I think it's probably CCDs are pretty much the state of the art. But in commercial imaging applications, Cmos imaging devices, which are roughly speaking, and this is very rough, I'm not an expert on Cmos, but they're basically like dynamic RAMs, only they don't put a cover on the top so that the light particles can charge the capacitor. And then when you read the capacitance like you would in a memory, you basically read the charge, the amount of light that's been collected in that cell. So the nice thing about CMOS devices, well, it used to be that CMOS devices weren't as accurate, but there's been a lot of advances in the technology. So even now the high-end, like I think the camera I described to you, the DLS, digital SLR I showed you, I think that particular one has a CCD. But a lot of high-end SLRs now have CMOSs, which has really been a major step for CMOS. CMOS is what is used in all the little cell phone cameras and the low cost cameras that are commercially available because they're inexpensive and they're also low power. Okay, but in any case, each cell measures basically a value which is proportional to the number of photons that have hit that cell over some period of time. So you get a measure, the impulse response or the point spread function of the cells, roughly a rectangle, because either it's sensitive, if a photon hits, if it hits inside the cell, there's some probability of it being detected by this cell. Now there might be a little bit of crosstalk between adjacent cells, but to the first order, the impulse response of this system is just a rect. Okay, so it's a little square. Yeah?
So each cell here is a unit.
Yeah.
But then it is T, so it includes some pixel. It is not one pixel.
So one cell there represents what you read out as a single pixel. And by the way, there might be some inefficiency. Like you try to design the electronics so it doesn't take up much room, but and sometimes you make them thin and they can be like transparent so that the photons just go through. But there's usually some loss at the boundaries, so it may not fill this region perfectly. And that's viewed as bad. They want the cell to be as large as possible. They can't really overlap. Or I don't know of any current technology where they overlap. So you get sort of a hard boundary between them. I'm not sure if I answered your question really.
My question is, compared to the pixels, the image, is it each cell is representing a 1 pixel?
Well, you see, that's a very good question. And I think the basic answer is that I want to say the answer is no. Okay, and sort of from a casual point of view, the answer is yes. Okay, yeah, sure. People take these values, then that's a pixel. They display the image, and you're good to go. Okay, but if you want to look at it in a more deep sense, then first of all, it really begs the question of what is a pixel? Okay, and it doesn't have a very clear answer. Okay, it's sort of like I think therefore I am, or something. I detect photons, therefore I'm a pixel. Okay, so I don't know what a pixel is. A pixel is what really is true is this: when you're trying to represent an image, and you're trying to represent it on a computer, you represent it with stored values. Okay, so these are stored values, but they're not necessarily the stored values that you're going to want to actually display to get the best image. So what a pixel is, I'm not exactly sure. But this is not the measurement of the image at a single point, which is sort of the way you often think about an image, okay? So we're going to talk about this. In fact, you're begging the question that we're going to discuss next, which is how do you convert this, okay, to to something that you would then display accurately. Okay, we're running out of time at this point, but I think we'll come back and finish this up next time, and see you on Wednesday then. Thanks. Bye.